Good afternoon, everyone. Welcome to the fifth class of reagents in organic synthesis. In this class, we will going to discuss about organolithium reagents, Grignard reagents, sodium-based reduction, and boron-based reagent chemistry. So first, I'm going to discuss about organolithium reagents. So organolithium reagents is organometallic reagents where carbon is the organic part and lithium is the metallic part. So if we consider about the electronegativity of any carbonyl compounds and organolithium compound, so we can see that in a carbonyl compound such as formaldehyde, the carbon is electronegativity of carbon is 2.5, whereas oxygen is 3.5. So in this case, oxygen is more electronegative. So it pulls the electron from the carbon to oxygen. So the dipole moment occur from carbon to oxygen. So in for that, this carbon is electrophile, electrophilic. So here nucleophile attack. So in this carbon center, nucleophile attack. If we consider about the organolithium reagents, what is happen here? The electronegativity is different here. So here carbon is more electronegative. The electronegativity is 2.5, whereas lithium is less electronegative 1.5. So we all know that lithium is a metal, so it tends to give it electron. So that's why it's electropositive in nature. So here, as the electronegativity of carbon is much more than lithium, so it will attack. So it can act as a nucleophile. So it can act as a nucleophile. So methyl lithium, butyl lithium, this kind of organolithium reagents are react with any kind of electrophile such as here carbonyl. So if we consider about the reaction of cyclohexanone with N-butyl lithium, so this is N-butyl lithium, as this butyl group, this butyl group 1, 2, 3, 4 is electronically positive, negative, and lithium is electronically positive. So, and here carbon, in case of carbonyl, this is electropositive and this is electronegative. So now react happened here, and after treatment of water, we will get this kind of product, this alcohol. So butyl lithium react with the carbonyl and form this tertiary alcohol. So if we consider about the molecular orbital diagram of carbon lithium compound, so lithium has 1s2, 2s1, and carbon has 1s2, 2s2, 2p2. So if we consider about sp3 bond, say as carbon form 4 sp3 bond with any kind of, say you are considering as carbon lithium bond. So here the sp3 has 4 2s2 and this 2 and this 2, 2s2, 2p2. So 4 sp3 orbital, and lithium has 1 2s orbital. So we are considering 4 for carbon and 1 for lithium. So it will form one sigma bonding orbital or one anti-bonding orbital. So in these cases, these three react with 3 hydrogen, this 3 electron, and 1 electron, and this electron form a sigma bond, that is sigma as bonding orbital, and one antibonding orbital. So this is the molecular orbital diagram of carbon and lithium. That's why they form bond. Now, organolithium reagents has 4 type of behavior. It can act as a base, can act as a lithium halogen exchange reagent, can do transmetallation and nucleophilic attack. So we considered all the 4 possibilities. So first we will discuss about basic nature of organolithium reagent. So if we consider this alkyne, this alkyne, so this is sp proton. So this is acidic in nature. As butyl lithium is butyl minus and lithium plus, so it can abstract this proton and from this negative charge minus. This will react with lithium plus, so it form the bond. So this will form the CLI bond. Now, now in presence of any electrophile, this base can react. So now as it has this minus and Li plus, so it will react with any kind of carbonyl compound and form this kind of alcohol. So if you consider this example, so here as alkyl is sp hybridized, so it is acidic in nature. So this ethyl magnesium bromide or any kind of butyl lithium or methyl lithium, any kind of lithiating reagent, Li plus, methyl minus. So it can abstract this proton and generate this minus MgBr plus or lithium plus. And in presence of formaldehyde, so this is formaldehyde. So it react with the formaldehyde and from this O minus, this will react with the water and form this alcohol. So this is the basic nature of organolithium reagent. So it can act as a base fast. So in any reaction where is a possibility of abstraction of proton, so it will first abstract that proton. Next, we will discuss about lithium halogen exchange reaction. So, in presence of any kind of primary, secondary, or aromatic bromide, so that's such as this one also, or aromatic bromide also. So, butyl lithium react with this and form this negative charge and butyl bromide. So, this will react with lithium plus, form this kind of aromatic lithiated compound. Whereas in presence of this butyl bromide, it will react with tertiary butyl lithium. So it will form the minus plus. So it will abstract this one and form this negative, which react with the lithium plus and form bond. So that's why it will form the butyl lithium. So now if we consider the reaction, so first in presence of butyl lithium, this aromatic bromide has to undergo lithium halogen exchange. So it will the butyl minus negative react with the bromide and form the negative charge and lithium plus. Now in presence of zinc bromide, so this is zinc bromide. So now this negative charge react with the zinc center and bromide minus ion will liberate. So it will form this one. This is an two type of reaction. So also this zinc is electropositive as it is metal. So it can react as a this aromatic can be minus and zinc is a electropositive, so it will be electropositive plus. So it will further react with any kind of electrophile. So it will react with carbonyl center and this will liberate leading to the formation of this product. So the important reaction of organolithium is the transmetallation reaction. So this transmetallation reaction, what is happen here? So first in presence of any kind of uh, alkyl bromide or aryl bromide, so this will form the lithium exchange reaction. So first this organolithium reagent is formed. Now, in presence of a metal, such as transition metal, here it is copper bromide, copper chloride, or copper iodide, any one, or any other reagent such as tin. So, it will form the negative charge will react with the copper and bromide leaving group as a leaf. So, it will form this organocopper reagent. So, now this organocopper reagent is very useful uh, for organic transformation. So, it can use as a Gilman reagent. So, this is called Gilman reagent. So, any kind of R2 copper lithium. So, copper is negative, lithium is positive. So, R2 can be anything, methyl lithium, methyl, R, R equal to methyl, ethyl, phenyl, any kind of reagent. So, in presence of alpha beta unsaturated ketone, what happen in these cases? In presence of alpha beta unsaturated ketone, this kind of Gilman reagent undergo a 1,4 attack rather than 1,2 attack. So 1,4 attack preferentially happen there. So this is because of the soft hard interaction. So in any alpha beta unsaturated ketone that can undergo resonance. So this is the soft position as it is undergoing resonance. The uh, electron cloud is moving through the bond and the carbonyl center. That's why it is soft. But in case of any kind of carbonyl such as this, so here the electron cloud is fixed between the carbonyl and oxygen. There was no resonating form. That's why it is hard. Now, due to this copper lithium complex, this this is behaving as a soft reagent. So now methyl react with the fourth position or Michael fashion, giving this enolate, which undergo resonance, giving this negative charge, and after acidic workup, we will get that conjugate addition product. So this is the Gilman reaction. So if we consider the example of this one, so here what is happening? This methyl is in alpha form. So if and in presence of Me2Cu reagent, Gilman reagent, we are getting this methyl react with the beta orientation. So what is the reason for that? So if we consider this transition state, so this is the cyclohexane, this is the carbonyl. So what is happening here? Methyl lithium is this one, methyl lithium. Now, no, I'm cleaning, I'm writing here. So this is the carbonyl and the methyl is the alpha. This is the methyl. And this is the hydrogen. So when now there is a possibility that it attack from the axial orientation as this methyl is in a equatorial orientation. So attack preferentially happen. Sorry, not in the carbonyl center. So the so now this this will react with the 1,4 fashion through axial and through axial orientation. So as methyl is a equatorial position, so attack preferentially happen through the axial orientation. So it will giving this one. So after tautomerization, it will form ketone. So now if we see the orientation of these two methyl, so this is in equatorial and this is in axial. So it is in alpha position and this is in beta position. So that's why you are getting beta attack product. So this that's why the stereochemistry matters here. So here also this is a Gilman reagent. So in presence of this apps, this oxygen is alpha. So that attack preferentially happen through beta. And now this was trapped by this after this metal lithium is formed and then it will trapped by the this reagent. Then we are getting this product. This is another example. So this is Gilman reagent is very important and the reaction of the stereochemistry also important. So now organolithium can react as a nucleophile also. So here R plus, R minus, Li plus. So now in presence of formaldehyde, it will R H. In presence of proton, it will from RH. In presence of formaldehyde, RCH2H alcohol is from. In presence of aldehyde, it will form this secondary alcohol. In presence of ketone, it is from tertiary alcohol. In presence of ester, so R minus react with the ester, it will go like this way and both R2 will leave. So this will form ketone. Cyano group also R minus Li plus. So it will react with the cyano center and it will go like this way. R1 C double one NH this R. And after hydrolysis, it will form this ketone. It will also react with the carbon dioxide. So R minus will react with the carbon dioxide. So this is from this acid. Now this further reaction of this RLI from this ketone. So epoxide ring opening also possible in presence of organolithium reagent. So R minus will react with this epoxide and this will open up. So this will give this alcohol. So this is also important. So in presence of this kind of chloride, so it has this proton. So Li plus. So now this negative this negative charge abstract this proton and this minus HCl or LiCl will leave from this benzyme. Now as system has this phenyl lithium, so it will react otherwise this way or this way, giving this mixture of these two products. So now I am going to discuss about Grignard reagent. So Grignard reagent is also a organometallic reagent. Organometallic reagent. So here metal is magnesium. So same as lithium, in presence of carbonyl compounds, it will form primary, secondary, or tertiary alcohol. In presence of acid derivative, after workup, it will form this tertiary alcohol. In presence of cyano, it will form the ketone, same as lithium. It will react here, and after hydrolysis, give ketone. Same as carbon dioxide, it will first give this acid, and acid can be further give form to carbonyl. So what is the mechanism here? Two type of mechanism can be possible. One is the concerted pathway, one is the free radical pathway. So what happened in the concerted pathway? So as magnesium is electropositive, so if we consider the partial positive charge and partial negative charge here. So now as oxygen has lone pair, it will react with the magnesium center, as magnesium is partially electropositive, and the R minus reacting with the carbonyl center. This is the cyclic transition step, and this is giving this alkoxide. This alkoxide after workup giving the alcohol. So in case of, if we consider the free radical pathway, what happens is there. So magnesium, as it is metal, it first react with the transfer the single electron to R. So it will form R radical. So this radical react with the carbonyl center in a radical fashion, and this will go. So now this is after workup giving this alcohol. So this is the radical pathway and this is the concerted pathway. Both can be possible. So it is very fast reaction. So we can't tell what is happening in the reaction mixture. So this is the example of Grignard reagent in the preparation of natural product. So first, in presence of C6H13 MgBr BF3 ethylate. So what happens is there is this is cyano group, say triple bond ring. Now in presence of BF3, the nitrogen has lone pair. So BF3 is a Lewis acid. We all know. The nitrogen can react with the boron and activate like this way. So BF3 minus, and as this nitrogen has lone pair, so it will the electron cloud will push and kick out this cyano group, giving this ammonium salt. Now this methyl magnesium R MgBr, R minus MgBr plus, quenching the ammonium and giving this product. This is also an example. So what is LDA? LDA is lithium diisopropyl amide, N minus Li plus isopropyl amide, diisopropyl amide. So it can act as a base. So as OH is first abstract this OH proton and from this phenoxide O minus. Now this O minus can react with the magnesium center and form this kind of complex. So now this will transfer to the 1,4 fashion and giving this force. So by this way, magnesium bromide can react with a 1,4 fashion or 1,4 addition product or Michael addition product. So if you consider the stereochemistry of any kind of methyl lithium or methyl magnesium bromide attack product, so that can be concluded by Cram's model. So if we all know that. So what happened in this model? So the most important conformation of carbonyl compounds with a stereogenic center adjacent to the carbonyl group are that the place of the largest group perpendicular to the carbonyl group. So if a carbonyl group has a stereogenic center, so this is the stereogenic center, three different group are there. So that is the chiral center. So what happens is there, the group which has the larger group are perpendicular to the carbonyl. So this is the Cram's model. Why this is perpendicular to the carbonyl? If this is not perpendicular to the carbonyl, such as if we consider this example R, so this is the perpendicular either this way, large group, or either this way. So these two perpendicular position can possible for Cram's model. What why this large group is perpendicular? So this perpendicular position, this conformer lowers the energy of the system. So if it is not to the perpendicular position, what happen in this case? So if it is in the this way or this way or this way, so there is a possibility of steric hindrance between this R group or carbonyl oxygen group with the large group. So that's why this is in the perpendicular position to minimize the steric hindrance. So this is the two possibility. Now nucleophile can attack with this position or this position to minimize the steric hindrance. So depending on the what type of nucleophile we are using. So there is a term called chelation control stamps model. So this is important here. So what happened in this case? This is a stereogenic center. So this OR is the large group, methyl is the medium group, and hydrogen is the small group. So this is a stereogenic center in beside a carbonyl group. So in presence of methyl magnesium bromide or dimethyl magnesium, what happens is there? So you can predict this type two products. So this is the major product and this is the minor product. So the major product from why? So this is happened through chelation control. So first, if we consider the Grams model, so uh, the large group should be perpendicular to the carbonyl. So either this way, the large group is over hydrogen, methyl, or this conformer. So either this side or this side. So now which attack will prefer? So if we attack either in this side, so large group and phenyl steric indents also matter. If we react with this side, the methyl and this phenyl interaction also possible. So this cannot be the perpendicular position. So if we consider this perpendicular position, so here if we react, so here hydrogen and methyl group are there. So this attack is unhindered attack, but this not happen in this case because it will go through chelation control mode. So as oxygen has lone pair, so and carbonyl also has lone pair, so it will in presence of magnesium methyl dimethyl, so it will form this kind of chelate. So due to this chelate formation, so there is a two possibility either nucleophile at in this side or this side. So this side is sterically hindered due to the phenyl and methyl group. So this is the sterically less hindered due to the chelation control. So what happen is there? What kind of product will form? So nucleophile is the methyl minus. So first I'm writing down this over. So now what happens is there as methyl is reacting. So methyl is reacting this side, this OH, this OH will form and this phenyl will go. So if we consider so very right, phenyl. So now if we continue to do the rotation of this will go here, it will go here, so it will form. the longer carbon chain in the same plane, the methyl and this phenyl, which so this will go, this hydrogen and OR will come here. Now we will write this in this. So methyl hydrogen one, and this will go methyl with. So it will give this compound one major product. So this is explained by the Cramps model. So Cramps model in case of the larger group should be perpendicular to the reaction to the carbonyl to minimize the energy state. So but in presence of chelation, such as if there is a OR group or any kind of group that chelate, so due to the chelation the chelation control product should be the major product. So now we'll discuss about sodium based reagent. So first I'm going to discuss about acetylene condensation. So in these cases, two ester molecule uh, dimerize to each other, and from this acetylene or alpha hydroxy ketone. So in these cases, sodium or molten sodium is used. So what is the mechanism? So first, sodium transfer a single electron to this carbonyl ester, and this will form this negative charge, and these two radical dimerized, and after leaving of this OR minus, this is from this diketone. Now sodium further react with this carbonyl center and form this negative charge through single electron transfer. So this is from this diradical 2 minus 2 minus this radical. Now this radical from a double bond here. After protonation, this indiol formed, and after tautomerization, this or this, anyone. Tautomerization, this acetylene and alpha hydroxy ketone will form. So this is one example. So what happens there? OET. This is the this is intermolecular. This is intramolecular. So what happens there? This radical this radical will form fast. That will make a bond. O minus OET. O minus OET. Further, OET will remove or leave. That will give this diketone. So now this diketone further react with the sodium and form bond. This this will form. So now in presence of TMS chloride, so this O, O minus will react with TMS chloride. It will react this way, and chloride will leave and form this di-TMS protected compound. So in this case also C double bond OMe. So here react, and this will form this O minus. So now this radical and this O minus will form. This can further react with sodium and form this carbon anion. This carbon anion react with the C3 carbon and leave the bromide, giving this cyclopropane. And this O minus is trapped by the TMS. So if we consider about the boron-based reagent, so the important reagent in boron-based is the carbonylation reaction. So boron is a vacant p or has boron has vacant p orbital. So now this carbonyl or carbon monoxide react with the vacant p orbital of the boron and form this Lewis acid base complex. So as boron can accept electron, so it is a Lewis acid, and this carbon monoxide is reacting, and that's why it is a Lewis base. So acid base pair will form. Now what happens is there. So now to neutralize this system, so this are moving to the carbonyl and neutralize this system. Now this is now in presence of lithium aluminum hydride, this hydride will transfer here and this will react with the aluminum. So this monomigrated product will form. First, this migration happen. After that, with the lithium aluminum hydride reaction, this monomigrated product. Now, what happened in presence of H2O2 NaOH? So, in presence of H2O2, it will react with the boron and form the negative charge here. So, it will form B minus O2. Now, this entire group to neutralize the system migrate here. So, it will form OB, whatever the group R, R, O minus, aluminum plus, H, R, L. Now after hydrolysis, it will form the alcohol. So this alcohol is formed. This alcohol is further reacting in this way and leave this alkoxide. So it will finally form this aldehyde. So in presence of H2O2 NaOH, what happened further if we use lithium aluminum hydride and H2O2? So first it will form this aldehyde. So in presence of LAH, it will further reduce to alcohol. So this is the mechanism of H2O2 reaction, H2O2 NaOH reaction with boron complex. So how it is formed this alcohol. So first H2O2 react with the boron center and form this. Then this group is migrating, one to shift is happening, and from this oxide further reaction of water giving this alcohol. This is also if we after carbonylation. So this is the intermediate. So if we not used any hydride source, I mean previous cases. Sorry. So in the previous cases, we are using the hydride source. The hydride will attack here, and the aluminum is reactive coordinating with the O minus. But what happened in these cases if we not used any hydride? So if we use water and heat it, what happened? So that H2O will react the boron and this negative charge will form tetra-coordinated boron. Now to neutralize the system, this monomigration happen and giving this alcohol. So after treatment with H2O2, this will form dialcohol R, C, R, OH, and further leaving of the liberation of water giving this ketone. Now I'm going to discuss about some problem. So first is the correct combination of reagents required to affect the pollen conversion. So this is alpha hydroxy ketone, alpha hydroxy ketone. This can be generated through acetylene reaction. So acetylene reaction is the sodium based reaction. So where is the example? Sodium xylene methyl pentacrylate chloride heat HCl plus sodium xylene heat. So this will be the right answer. So what happened is there COOMe COOMe. Now sodium transfer its single electron to this and form this diradical. Now this diradical will make a bond here, and after liberation of this OMe giving this diketone. Now sodium further react. This single electron transfer happen here and here. It will give that radical make a bond O minus O minus. Now in presence of trimethyl chloride, so this OM minus will be protected by the silyl group. So OMe, OSiMe3, OSiMe3 will be formed. So it will not give this alpha hydroxy alcohol. But in absence of any silyl reagent, so it will form this OH. Now after tautomerization, giving your final product, this alpha hydroxy ketone. So I'm erasing this one. So correct answer is the B. Now the next question is that this under magnesium dry ether will from the al- alkyl magnesium bromide. So Me3 SiEH MgBr will come. So this is electropositive. This is electronegative. Now in presence of benzaldehyde, this will react and give O minus SiMe3 pH. Right? So now in presence of aqueous medium or H2SO4, so it this O minus can react with the silyl. So 1,2 group rearrangement happen. It will go like this way and leave in this. So this or other way, it can react with the trans fashion, so giving the trans stilbene. So cis stilbene and trans stilbene will form in this reaction. The alkoxide react with the silyl group and leave the silyl reagent. The next question is the major product sodium ammonia minus 78 degrees centigrade. So sodium can transfer a single electron. So here and this will go. So this can this minus radical This radical is formed. Now what happened? A radical rearrangement can be happen. So this will go like this way, this will go like this way, and this way. So it will whatever the group are there. So the O minus, then whatever the group are there, this radical. Now this radical further can abstract a single electron from sodium and from this negative charge. This can be react with the ammonia or extract proton from ammonia. So which will form this intermediate. So now this intermediate, this will go like this way, and this is from this negative charge. So this dot negative charge will form. So now in presence of methyl iodide, this negative charge react and iodine will leave. So it will give this product. Now the what will be the stereochemistry of this methyl? So what is happening is there this anchoring group, this methyl CH2OMe is the beta orientation. So now the negative charge has to react with the methyl iodide. So as it is in the beta orientation or up position, so the methyl come from the down or alpha orientation. So it will give the alpha alkylated product. Due to this beta methoxys to OMe group. So ketone, whatever the group and methyl. What is the answer then? So this the first is the right answer. Next is the methyl this double bond magnesium bromide with the ester. So this is the negative, this positive. So the one negative will react with the carbonyl of the ester. This will go and OMe will leave. This give this one. Now in presence of Grignard reagent, excess Grignard reagent, negative, positive. So it will further react with this carbonyl center and form the ketone. Methyl OH. So it will give this product. Now also Grignard reagent. So what happens is that this is the electropositive and this is so in presence of fluorine, alkene, fluorine, alkene and oxygen, go double bond group. Me3 Si CH2 MgCl plus minus. So this will react with the alkene and this negative charge trapped by the oxygen. This will give Chilyl group and this will form this O minus. So which in presence of water work up from this alcohol. Now this peroxide bond can be broke in presence of water, which will give the furyl alcohol. This Me3. So the right answer will be the third one. Me3Cli. So iodine is there, so and lithium is there. So there is a halogen exchange reaction. Halogen exchange. What happened in these cases? Is little one CH2 CH2 1 2 3 4. So that's Me3C minus Li plus. That will react with the iodine and this negative charge will form. That will abstract by the lithium. So this will form. Now what happened in presence of bromine? So while if we attack this in presence of bromine, what happened? So the pi electron cloud of the alkyne react with the bromine and divided one bromide minus, it will give pH double bond bromide plus 1 2 3 4 1 2 3 4 1 2 3 4 lithium. So now this is extracted by the bromine. So bromonium intermediate will pop. So bromonium intermediate will pop. pH Br plus CH2 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 1 2 3 4 minus lithium plus. Now this negative charge react with this bromonium intermediate and neutralize this bromine. So this will give this 5-member ring with pH here. So after neutralization, this will come. Now what happens there? This is also metal halogen exchange reaction. So in presence of butyl lithium, butyl minus lithium plus metal halogen reaction happen. This will be a butyl minus react with the bromine, bromide and negative charge will form. So I'm just writing the only benzene ring. Okay. O isopropyl methyl OMe. Then So this will from this the R Li will be from. So this is negative, this is positive. Now what happens is there this negative charge in presence of TEMDA, tetramethylene. So tetramethyl ethylene diamine. So what is the role of TEMDA? So it abstract the lithium ion. So it will coordinate with the lithium and and it will coordinate like this way with the lithium. So now if it is coordinate with the lithium, so this negative charge is now free. This negative charge is now free. So as it is free, it is highly reactive. So it will react intramolecularly with this carbonyl carbon, ester carbon. This will go like this way, and um, this this lactam bond will reopen. So it will pop 1, 2, 3, 4, 5, double bond group, CH2, CH2, OH. Whatever group is there, O isopropyl, methyl, OM. So this is the right answer. So after with lithium halogen exchange, so the negative charge is highly reactive after extraction of the lithium plus with the PMDA. So this will react with the ester carbonyl and ring open. So this is the epoxide ring opening of methyl magnesium bromide. So CH3 minus magnesium bromide plus. Now there is a two possibility attack. One is this side, one is this side. So this is sterically hindered. This side is sterically hindered due to the ethyl group. It will react CH3 minus will react in this side and this epoxide ring will open. So now as if we consider the epoxide ring, so as it is in beta orientation, this epoxide is in beta orientation or which orientation or up orientation. So this methyl should be come from the down, should be come from the down or alpha orientation. So this OH and methyl will come from the down or alpha orientation. So this is the right answer. Now what happened in Wurtz-Fittig reaction? Which metal is used and follows which metal is used? So what is Wurtz-Fittig reaction? So what in presence of alkyl halide or aryl halide, so such as this one aryl halide plus any kind of alkyl halide, in presence of sodium, so the alkyl and aromatic will react and form a bond. So what happened in this case? So this is done through radical reaction pathway. So the sodium must transfer a single electron and liberate the bromine. So it will form this radical. Now this radical in presence of another sodium abstract one single electron and form the negative charge. This anionic carbanion for which will in presence of methyl bromide react with the methyl bromide and liberate the bromide ion and form this aryl with alkyl coupling product. So it goes through sodium and predecker pathway. What's the last question? So the alpha beta unsaturated ketone in presence of ethyl magnesium bromide, cerium 3 plus, and ethyl magnesium bromide copper iodide. What happened in cerium 3 plus? So in presence of cerium 3 plus, cerium is the Lewis acid. So oxygen is has lone pair, so it will react with the cerium 3 plus. So Lewis acid base pair will form Lewis acid base pair. Now in presence of ethyl magnesium bromide, ethyl minus magnesium bromide. So at this oxygen is attached to the cerium 3 plus, so the electropositivity of the carbonyl group enhanced due to this Lewis acid base pair. So it is now further highly electrophilic in nature due to the Lewis acidic coordination. So now this methylene will attack with the carbonyl group and form this alcohol. What happened? So this is 1-2 attack happening here. 1-2 hard attack. Carbon is also hard and ethyl magnesium bromide is also hard. But in the presence of ethyl magnesium bromide and copper iodide, transmetallation happen and it will give ethyl copper magnesium bromide. So which is soft. So the magnesium ethyl negative charge, copper is also negative charge, magnesium is positive charge, bromide is negative charge. So this is due to this soft nature, this ethyl will react with the 1,4 pressure, 1,4 pressure. So soft interaction, the driving force and giving this alkoxide. So this is quenched by water, giving this product. So what is the answer? So the first one is the right answer. If you have any question, you can ask. If you don't have any question, I'm closing today's session. Bye bye.